My name is Seth Kinoshita, and this is Lab 4, Oscillations and Energy. Today, I will be covering the introduction and the purpose of the lab, as well as some basic physical principles. Then I will go into the experimental and computational models and the results that I got, as well as some possible errors. Finally, I will wrap up with what my results mean. So the purpose of the lab was to extract position data of a mass hanging from a spring and, using the energy principle in a computational model, compare the experimental and the expected position of the mass at various time intervals. So the first physical principle is the spring force. There are multiple parts to the spring force, and an important one is K, the spring constant. This is measured in newtons per meter and is unique to every spring. Additionally, every spring has a unique relaxed length L0, or the length that it will be when no outside force is affecting it. And the spring force will always point in the direction towards its relaxed length, seen in the diagram to the left. So if the rest length is here, but the spring is stretched, the force of the spring will go back up towards the rest length. However, if the rest length is compressed, the force of the string will always be down. In the case of this lab, with a vertical string and a mass, it will oscillate until it reaches an equilibrium point with a distance L away from the origin. An important thing to note is that the spring force is a non-constant force, as it is affected by how far the spring is stretched or compressed. And the formula is over here, where it's K is equal to F over X, or F is equal to negative K, L minus L0 times L hat to indicate direction. The second physical principle is the energy principle, and the energy principle states that the change in energy of a system is equal to the total work done on the system. Since work is equal to the change in kinetic energy, the total change in energy is equal to the change in kinetic energy. However, you must also account for the change in potential energy of a system depending on how it's defined. In the case of this lab, the system is defined as the spring, the mass, and the earth. This leaves nothing in the surroundings, and thus no external work is done on the system. Therefore, the total energy of the system must be equal to the kinetic energy of the mass plus the potential energy of the spring and gravity. And the formulas for potential and kinetic energies can be seen over here, where kinetic energy is equal to 1/2 mv squared. Potential energy for the spring is equal to 1/2 k delta x squared, where delta x just represents the displacement of the spring, and potential energy of gravity is equal to mgh. So the experimental data was seen here, where it was collected in Tracker by tracking the point mass. A calibration stick was used to set the length L with the mass to 0.7, which was seen in the pre-lecture video. A graph and a data set were collected from the experiment. The initial conditions could be defined as the following. The position was determined to be the coordinates at t is equal to 0, and the velocity was the 0 vector. G is equal to 9.8, and the other constants were calculated or given in the pre-lecture videos. Finally, the mass of the object was determined to be 0.402 kilograms. So here's a look into the code for the lab. It's pretty simple, and it mainly centers around the energy principle shown here. The total energy of the system is defined as the sum of all three types: kinetic, gravitational, and spring potential energy. Additionally, position and velocity update formulas came back to iteratively determine the position and velocity of the mass at infinitely small time intervals. Finally, I utilized three different energy formulas seen earlier to model the position of the mass. So this is a graph of all the types of energy as time progressed. And while it looks like a lot of lines, two important relationships to point out is that when potential energy is at its maximum, kinetic energy is 0. Additionally, the total energy remains 0 for the entirety of the experiment. This will be useful knowledge later. And these are the graphs of both the x and y positions. The blue is the model, and the red is the experimental from the Tracker software. The model is somewhat accurate in predicting the position, but there are some noticeable discrepancies between the peaks and the troughs of each of the positions. One source of error could have been generalizing the period of oscillation in the code when it is different for both the x and y coordinates. Again, that will be useful later. Another source of error is that the system in the video is not actually closed, meaning that there are other forces present acting on the mass that are not accounted for in this model. To analyze this data, two questions were posed. The first is the energy principle satisfied? And the answer is most certainly yes. The total energy at any point on the graph is equal to 0, indicating that there is no external work on the system. Since we are treating this as an isolated system, it does make sense that there would be no external work. No energy in, no energy out, as indicated by this diagram over here. The second question is, how do the two oscillation periods for the x position and y position compare? And why would this be the case? So as seen below, the periods of oscillations were calculated for both the x and y coordinates, with x being 1.519 seconds and y being 1.709 seconds. And there is a noticeable difference. This is likely due to external forces acting on the mass, and implies that a different spring constant would be calculated based on the period of oscillation used to calculate it. This has ramifications on the lab itself, because a different spring constant cascades into multiple different calculations, changing the numbers every time. It would be best just to average these two numbers together in the long run.